hit both mute and like unmute and stop video, but I guess I missed it the first time.
Sorry. I don't know. That happened to me last week, so I thought that might have been what just occurred.
Oops.
But I can hear now, and that's all that matters.
Okay, can you see the desktop?
Yep.
Yes.
Okay. The things up. Okay. So first, I finally put up something for you to do as homework assignment. So I marked it as an exam/homework assignment. Okay. It's 4 problems, a combination of stuff that you can analyze and some code that you'll be writing based on mostly threads. Okay. So there's the first problem has you analyze this code and say something about it. Okay, so you have to explain what this code is doing. Okay, and then it asks the second part, asks you to rewrite it using condition variables. Like right now, it's written using semaphores. So have it do the same thing using condition variables instead of semaphores, and then yeah. So this one's got 2 parts. So what is it doing, and then rewrite it using condition variables. So it does, so that it still does the same thing. And then problem 2 asks, this code here implements this little graph here, in that this is a dependency graph where you're not allowed to do calculation D until B and C have completed. And you're not allowed to do calculation E until A and D are completed. So this is a dependency graph, okay? And so this code does that. Well, it's supposed to do it, but there's actually something wrong with it, okay? So you have to read the code. It only uses, this is essentially a baby version of fork join. It only does creating and joining, okay? So notice it only forks and joins threads, okay? And it tries to create them in that pattern. But there's actually a little mistake in there. So you have to figure out where the little mistake is, okay? And then part B asks you to, right now, this one is using 1 thread for every edge. So there's a thread that runs A, a thread that runs B, a thread that runs C, a thread that runs D, and a thread that runs E. So that's 5 threads. But you don't really need 5 threads because the idea is here, it's like 1 thread could do C, and that same thread could be, we talked about that in fork join. So a lot of times you can reuse a thread. So like 1 thread could do all 3 of those. So you don't need 5 threads, you actually only need 3 threads. Because there's 3 things that should run in parallel at the beginning. So A, B, and C are all independent of each other. So there needs to be at least 3 threads, but you don't need more than 3 threads. So right now it's using 5 threads, 1, 2, 3, 4, 5, and you can do it in 3 threads. So part B is to rewrite it using the minimum, you rewrite it using 3 threads. And then part C is to do it in Java using the actual fork join framework. Rephrase this as a real Java fork join problem, okay? Because it is only forking and joining, so it ought to be able to execute in a fork join manner, okay? And this kind of graph is sometimes called a data flow graph. So this is thinking of fork join as data flow. The data flows through the graph in a certain dependency. So that's one way of thinking about parallel programming. You can turn this into a you can turn you can turn a problem like this into a whole theory of parallel programming, what they call data parallelism. Okay, but this is just one little problem. It's a kind of a cute problem, like, implement that dependency. And you don't need fancy synchronization to do this. This kind of dependency can be done just with fork and join. Okay, so then problem 3, same problem, but with a more complicated graph. Okay, there's more nodes and they depend on each other in a slightly more complicated way. And I ask you to do this, and you can use any synchronization mechanism you want, whatever you think will work to get these. Now, these functions don't do anything. I point, what you should just do is the actual body of the function should be like just print I am A, I am B. You know, you can, or you can have like a little sleep. You know, the body of each function could be sleep a random out, print I am A. Okay, so we're just trying to simulate we're really trying to simulate the ordering. We don't really have these functions doing anything yet. So this is pretty common with this kind of stuff, with homework problems like this. Just treat each thread as something that sleeps for a random out and then prints out its name. Okay. So here, you know, each one of these functions the function can just sleep for a random out and print its name, but you have to get them to run in this order. You know, notice that this means that D can't run until B is completed. Similarly, both D and F depend on B. F also depends on A, and D depends on C, and E depends on all of them. Okay, but specifically, it's depending on F and D. So E can run when F is completed and when D is completed. Okay, and it is synchronization. So you can create this synchronization. You can create it with semaphores, you can create it with mutexes, or you could try to create it with just fork join. Okay, so I said you can either do it as a C program or as a pthreads program, or a C program using pthreads, or as a Java program, but get that pattern there. Okay, and then 4 is a question about how do you implement a mutex. Okay, here's a class that supposedly implements a mutex. So, you know, the idea is, oh, let's write our own mutex. It's, you know, it's just it's a good exercise, but there's something wrong with it. There's 3 mistakes in it. So you have to find the 3 mistakes in this and then fix them. So you find the 3 mistakes and fix them. And then after you fix them, I want you to compare them to the mutex that's in pthreads. Does this mutex act like a pthread mutex or not? And it turns out pthreads has 1, 2, 3 different kinds of mutexes. There's the pthread mutex normal, pthread mutex error check, and pthread mutex recursive. Pthread actually has 3 kinds of mutexes. This is one of them. So I want you to figure out, you know, read the documentation, look at this code, and figure out, well, which one of the 3 mutexes in pthreads is this one acting like? Okay, so it's sort of it's a test. You know, you have to read the pthread documentation, and then look at this code and try to figure out which one of these 3, normal, error check, or recursive, does it act more like? Okay, and that's actually B and C are the same problem. B asks which does the lock function act more like, and C asks which does the unlock function act more like. And it turns out that this mutex acts like one kind of pthread mutex in the lock function and acts like a different one in the unlock function. Okay, and it turns out that when you read about it, it's a little bit interesting. We kind of presented mutexes as trivial, is that they just say mutual exclusion. But it turns out that mutexes are kind of complicated. There are a bunch of different ways you can implement mutex. It has mostly to do with things like what happens if somebody grabs a mutex twice in a row? What should happen when the same thread grabs a mutex twice in a row? What should happen when a thread that doesn't own a mutex tries to release it? You know, if you don't own a mutex and you go ahead and unlock it, what should happen? Well, you know, one thing is it could just ignore you. Another thing is it could crash you. You know, maybe, you know, and that's part of this is you have to figure out which one's happening here. Like, you know, and which one does pthreads do? Because sometimes you might say that, well, if a program released a mutex it doesn't own, that's really serious. We should crash the program to let the programmers know they did something really wrong. On the other hand, you might just say, who cares? If a thread releases a mutex it doesn't own, just ignore it. So the library could do either one. Pthread actually does let you choose which one you want. Pthread, by letting you choose which mutex to get, you get to choose which behavior you want. So one behavior is implemented in here, and you have to figure out which one of these pthread ones does it act like. Okay, and then part D just asks a question about the lock, about what's the difference between this piece of code and this piece of code. Okay, so it's just asking you to look at it's got to do with asking what does notify mean in Java. So you may have to look. We didn't talk much about notify. Notify is like the condition variable's signal. It's like the signal in a condition variable, but it's a little bit different. So notify in Java is kind of like signal in a condition variable, but not quite. So this one asks you to compare the unlock method up here. Notice it uses notify with what happens if you just call notify on the, what happens if you just call notify on the mutex instead of calling unlock on the mutex? What does that do? Okay, so that's a question, a little question to ask, you know, to look up what the notify method on a object in Java does, and how it's a little bit different, but almost the same thing as the signal method was on a condition variable. Okay, so there's 4 problems. You'll actually write code for a couple of them, and you'll write answers. Like this last problem 4, all the answers are just words. You know, the answer will just be writing up an explanation. When you submit your homework assignment, if you like tech, I provided the tech file here. You can, if you know how to use tech, you can put your answers directly into the tech file. There's places for you to put your answer in a tech file, and then you can tech it, and I'll get a nice document with your answers in it. If you don't want to use tech, you can just put your answers in any document you want. Word document, text file, web page, anything you want. You know, you have this many answers to give me. You can see there's an answer for, you know, you can see how many answers there are, but just if you want to put the answers in a Word document, a text file, anything is okay. And if you like tech, if you know tech, you can put them directly in the tech document. Okay, so that's why I put the tech document as part. You know, this is the PDF version you can read and print. And if you want to work with the tech document directly, you can go ahead and do that. Okay, all right. So this is due the last day of final exam week. So that's not this Friday, next Friday. Okay, that's the last day of final exam week, May 8th. Okay, and grades are due like the next Wednesday. So I think that'll give me enough time to grade it. So they'll have to be due that day because the grades are due in, was it like 5 days after that. Okay, so that's kind of a hard deadline, the 8th, because I have to start grading them right away. Okay, so that's a pretty hard deadline. If you have questions, you know, if you have questions about this, send me an email. You know, it's kind of a homework / exam. If you have questions, go ahead and ask me questions. The only thing I ask is that each person should work on it themselves. You know, mostly work on them on it yourself. Okay, do your own work on it. But if you have questions, go ahead and ask me questions. And you know, if you find some really good reference, you can share it with other people. Like if you think you have something that's good reading, I think it's a good idea to share with people something that's a good reference. Don't share answers. But if you think you have something that's a good reference to read, if you think there's something that would explain this, I think it's very fair to share references with each other, but not answers. Okay. Okay. So okay. So that'll be the last thing of the semester is for you to work on that. Okay. And I think it's 4 problems. I think you'll have time to do it. Okay. Okay. So what I want to do today is we've been working on these serial and parallel searches. Okay, so I'm going to show you some more. I've been writing the code for these and expanding on them. When we left last week, let me see. Let me open the folder we were. We were doing the searches on all the files. Okay, we were doing searches on all the files, and we had up to this search here. Okay, this is the one we looked at last Wednesday. Okay, and I've written a couple more since then. I've been able to speed this up, and I'll show you what I was able to do to speed it up. Okay. What this one did, okay, this little bit of code here opens all the files. There's 1,000 files. So this thing opens 1,000 files. For each file it opens, it calls this function here. Let's see. Okay. I'm trying to remember what we. Oh, there's a. I was looking for the pool. I forgot where the pool was. There's a static. There's a global thread pool because the thread pools get. I put the. Here's the tasks. Let's see. Oh yeah, the thread pool needs to be global because this function uses the thread pool. So the thread pools use, the thread pools, the main method isn't what really puts things in the thread pool. The main method for each file calls this method, and this method will open the file and then create a pool object to process that file, okay? So again, this doesn't open the files. This just gives us a path to each file. So this loop gives us a path to each one of the files, and then this function will actually open the file and then create a task out of it to search that file for aardvark, okay? So this function will take in a path. See, it'll take in a path. It takes in this, essentially the name of a file. It'll open the file, and then it'll read the file one buffer at a time, and for each buffer in the file, it creates a thread pool object. So each file can result in many thread pool objects. Okay, so we read the file one buffer at a time, and we create a thread pool object for each buffer. Okay, this was the fastest way we were able to do it when we did sequential. By reading one large buffer, and then by executing the search on one large buffer, remember what that did was it made the amount of time to read a buffer about equal to the amount of time to search a buffer. That gave us good balance between the I/O task and the compute task. So this was kind of tuned so that the amount of time it takes to read a buffer is about the amount of time it takes to search a buffer. Okay. If you don't do this carefully enough, if the amount of time it takes to read a buffer is way too long compared to the time it takes to search the buffer, then you don't get good parallelism between the two parts of this task. Okay, so read a buffer, then create a task to search the buffer. Then you immediately read the next buffer, then you create a task to search the buffer. The tasks run in parallel with the reading. So we have parallelism between the reading of the buffers and the computing of the buffers, okay? And then the task just, it's the same task as it was in the sequential search. The task just searches through one buffer, okay? This ran pretty fast. My machine's been acting weird. Okay, it took 15 seconds there. It should have run a lot faster than that. Let's see. Okay, notice this time it ran in three seconds. Okay, this time it ran in 3 seconds. Now, I have to do more playing around. You know, this one, the first time I ran it, it took 15 seconds. This one took 3 seconds. I don't know if my computer was acting weird there or if this was the operating system caching that large file. And that maybe right now it's running it out of the cache. But I've been running these for a while now. So if that file was cached, it should have been cached already. So I'm not really, you know, whenever you do this I/O kind of stuff, it's gets really confusing what's really going on. But right, see, it should run in usually about 3 or 4 seconds. See, there it ran in just under 3 seconds. Okay, and it'll run, it'll probably continue to run under 3 seconds unless my laptop kind of burps. My laptop earlier this afternoon kept crashing Explorer. You know, Explorer that draws the desktop. I had Explorer crash on me 3 or 4 times in a row. Like I was trying to copy files and Explorer kept crashing on me. I probably should reboot the computer. So, but it's been acting kind of flaky. Okay, so that one long time, that run took 15 seconds, and that was 5 times longer than these other runs. I don't know if that's because the machine was caching the file, but I don't think so, because just before class I ran these a few times, so it should have cached the file. I think it was just slow for some other reason. Something else kicked in. Okay. By comparison, here was, oh, okay, all right. So now, how can we speed this up? Okay, so I was like, how can this get speeded up? Okay. Let's see, now let me show you the next version. Okay, 2 seconds. Okay, so I was able to get it from from 3 seconds down to 2 seconds, which is not bad, because that's a 30% increase in speed. That's not trivial. So let's see if we can analyze what I did to get this. Now, if the file was bigger, that would show up as a lot more. I mean, that is literally a 30% increase in speed. So that's pretty big jump in speed. It doesn't look like much here, but if I keep, like now, if I went from a 2 gigabyte file to an 8 or 10 gigabyte file, this would start looking quite a bit different. Yeah, a 30% increase in speed is quite a big jump. Okay, now what I did is this final version is using a fork join pool. Okay, instead of using a regular pool, instead of using a regular pool here, where's the pool? I'm sorry. Instead of using a regular one of these executor pools, kind of a fixed thread pool, I switched to a fork join pool. Okay. Okay, let's look at what it does. This, like before, gives us a path to every one of the. Oh, actually, see, here's here's. Go back to this one. Okay, we get a path for every file. Then this program, in serial, not in parallel, it steps through the buffers. So it's actually reading the file sequentially, okay? So it reads one buffer full and then creates a task. Oh no, I'm sorry. This is, think about what this does. You get the list of paths. Then for each path, you'd call this function. Okay, that's done sequentially. You get the first path, then you go down here and you fork off, you search that path, but you take that file, you step through it, creating a bunch of tasks. Then you go back up here and you get the second path. You get the second path here, you go down here, and you get that file, and you go through all its buffers. But notice that this is a sequential loop. Okay, it loops through one file at a time. Then when it gets a file, it goes down here and it reads the file sequentially, and it parallelizes the I/O between the reading and the, it parallelizes the I/O on that one file with the tasks on that one file, but you're only processing one file at a time, okay? So we're only processing one file at a time. Not quite though. Like once we've started all the compute tasks on one file, before they're done, we could start another file, but we're doing these files one after the other, okay? Now what this one does is says, once I've started working on one file, why can't I immediately start working on another file with another core? So over here, for each file, I put something in the fork join pool. Okay. Notice that now for each file in the directory, I execute on the fork join pool a task for that file. Okay. All right. So now I've got a task for each file. Now, what does that task do? That task steps through the file, and this is the tricky part. This is the part that's real interesting. For every buffer, it forks off a new task. Okay? Okay. Notice that it's forking a new task into the fork join pool for every one of the buffers in this one file. So now we're processing files in parallel, and each file itself is processed in parallel. Okay, so you go up here, for each path in the list, in the directory, we fork, well, actually, we don't quite fork. For each path, we start a task in the fork join pool. Notice that this is execute, so this is starting something in the fork join pool. So each file in the directory represents the starting point of a fork join process. Then each file will fork a bunch of subtasks, which are the buffers in that file. So this is really interleaved now. We've really interleaved a lot of I/O. We've interleaved the I/O of essentially opening. So you open a file. Now, one core is opening one file, while another core is going to be opening another file. So now we can have multiple cores opening multiple files because we have these. Each one of these tasks is put into the fork join pool by itself. Each path represents its own task in the fork join pool. So that means that two files could be worked on simultaneously. And then each file creates a bunch of subtasks. It creates a bunch of subtasks which are the forks of itself, which each subtask is reading one buffer full in the file. Okay? Notice that this is fairly abstract. You know, we've got two layers of forking going on. Well, we've got one layer of submitting to a pool. We have one layer that submits to a pool. And then when that thing is in the pool, that thing in the pool starts forking off more things into the pool. Okay, so the pool fills up with a lot of work. And the pool is filling up with a mixture of two kinds. I have two kinds of tasks now. See, one kind of task, I call it a task 2. This is the task that puts, that represents one file. And then this other task represents one buffer in a file. So I have two levels of tasks that are both recursive actions. So I have two levels of tasks, and this kind of task, this task forks off many of these tasks. But with this level of complexity, I get super speed up. You know, I've really got things fast now. You know, I've got now, I can process this 2 gigabyte. Notice I'm processing 2 gigabytes of data, 50 million lines of text in just 2 seconds, which is pretty fast. You know, it's processing 2.3 gigabytes of text, which are 50 million lines of text, and it's processing them all in just under 2 seconds. Okay. Now, if you run it, you don't see the cores get busy because it's only 2 seconds long. to actually make to see the cores work, how the cores are 100% being used, I'd have to increase the size of this file from 2 gigabytes up to like 8 or 10 gigabytes. So instead of running for 2 seconds, it could run for 10 or 15 seconds. I haven't created a huge file yet, but it needs a lot of complexity to get the optimal speed. I'm pretty sure this is getting real close to the optimal speed. I bet it isn't yet. I think there might still be ways to speed this up. I'll tell you in a minute what I think might be a way to possibly speed this up. So I don't think it's as fast as it could be, but it's getting pretty close. Now, notice that this was version 5, this is version 7. There's an intermediate version that's kind of interesting because it didn't work. And it shows you, I thought this was real interesting because it showed why the fork join pool is so useful. Okay. We went from 5 to 7 by creating 2 layers of tasks. Okay. So what if I stuck with a regular pool and tried to do the same thing? What if I used a regular pool, not a fork join pool, and tried to do the same thing I did in version 7? I can do it, but it doesn't quite, there's a problem with it. Okay. So here, let's look at the code. Okay. Where's the beginning? Oh, I'm sorry. For each file, for each path, submit the path with task 2 into the thread pool. Same idea. So for each path, create a task 2 and put it in the thread pool. Task 2 in this case is almost exactly like it was in this case here. They're almost the exact same kind of task 2 and task 1. A task 2 opens the file, reads it buffer by buffer, and submits to the thread pool a task for every buffer. Okay, so we have a task 2 in the thread pool forking off task 1s. Okay, okay. So this is kind of looking like fork join, but I'm not using a fork join pool. I've got a task 2 in the thread pool that's branching off multiple subtasks. Okay. Now this works except for one problem. Okay. This code here and this code here is exactly the same as it was in the thread pool case. The problem is you can't shut down the pool. The problem comes with trying to shut the pool down. Okay. Okay. If I run this right now, it works. It's pretty fast, but I never shut the pool down. So right now the program doesn't end because the thread pool is running. The program doesn't end because as far as Java is concerned, the thread pool is still running, so the program's never going to end. Because I don't know how to shut the thread pool down. Like, let me show you now. Yeah, Andrew,
I ran across the same issue, and what I just did is instead of just tossing the tasks anonymously into the executor, I would toss them first into a linked list and then toss those into the executor and iterate through the list after I'm done, waiting for those objects to finish.
That might be
and it's very fast. It's
okay, actually,
not as fast as what fork join is doing, maybe?
I don't know. I'd have to see. I think I could do that. Like, okay.
But it's just extra code.
Right. So every one of these tasks I'd have a separate list, so I would remember all the tasks. Instead of anonymously putting in there, remember every one. Then when I'm done submitting them, I would, now let's see. But the trouble is, how would I would have to have a way of, I'd have to probably make them all futures. Because I would have to know when they're done.
That's basically what I had to do, is just implement
make
futures.
Them all futures. Then you could wait to see when they're done. And then when they're all done, you can shut down the thread pool. Now here, look what goes wrong here. Here's what I'm trying to do. I want to, this won't work like it does with the fork join pool.
Really?
Here's what happened. So what the naive thing to do is, after I put everything in the pool, tell the pool to shut down. Now Java's smart. When you tell a pool to shut down, it doesn't shut the pool down. What it
just
really
stops
does is
accepting new.
it stops accepting new jobs, right? So it lets the pool run until all the jobs are completed. So you send the pool the shutdown message. The pool no longer accepts new jobs. Then you wait for a long time, okay? And then you basically wait till the pool is, you basically don't, you wait for a certain amount of time that you think is sufficient, and then the pool is over with, okay? Now here's the problem with this. When you shut down the pool, it won't accept any new jobs. Task 2s are in the pool, but task 2s are forking off new jobs. So run this.
I see.
What's happened here is I've got to the point where the pool has been shut down, but many of the task 2s are still in the pool trying to create their baby tasks, but the pool won't accept them anymore. Fork join is very clever. I was really fascinated by this. I started realizing how clever the design of fork join is. When you shut down a fork join pool, it won't let any external tasks be submitted to the fork join pool, but it will let the tasks that are already in the fork join pool submit their baby tasks. It'll let the tasks in the fork join pool continue to fork. But a regular pool doesn't let you do that. A regular pool, it sees jobs in the pool, putting jobs in the pool as external jobs. So a regular pool, even though I'm already in the pool, when I submit a new task to the pool, that's seen as coming from outside. So if the pool has been shut down, this guy crashes. And I get all these, I get this reject executor service task. See, I get an exception where the task pool has rejected new submissions. Okay, so that's kind of clever of the fork join pool. The fork join pool says, okay, if you shut me down, I'm going to let the tasks that are already in me continue to submit new tasks to the pool. So that lets the task finish, but it doesn't let external tasks be submitted to the pool. But a regular pool, a regular task pool is kind of dumb. A regular task pool doesn't make a distinction between tasks that are in it and tasks that are outside of it. A task that's already in the pool, that's over here. Here's our task that's already in the pool. Our task that's in the pool wants to execute something in the pool and it can't. Okay? All right. So now, so that didn't work. Okay? Okay. So what now to make that work, I just did not shut the pool down. So I went back to just not shutting the pool down. If I don't shut the pool down, it works. Okay, but then I don't know when the pool's allowed, when should I shut the pool down? So then I could maybe use Andrew's idea of keeping, I would create every task that I put in the pool would have to be a future, and then I could keep track of all of them. I could wait till all these futures are finished, and then I could shut the pool down. Okay, when I knew that all these tasks here, which are the external, well, actually, then no, that would be more, no, it'd be more complicated than that. I'd have to wait till
those guys are done.
Yeah, I may have to wait till all of these
are
are done. But then that's a gazillion. That's a lot of.
That's a long list.
Yeah, like if you run this, okay, if you run this thing here. The fork join pool tells you how many tasks were actually submitted to it.
How many is that?
Oh, it doesn't.
Huh.
Oh,
does it have any steals though?
Yeah, it shows you. Yeah, I mean, normal thread pools. Actually, I can probably ask the fork join pool how many tasks were submitted to it. So its summary statistics don't include that.
it looks to be somewhere in the range of what you create one child task per line, right?
Yeah. So it'd be 50 million.
Then it's in the range of 50 million.
Yeah, it's in the range of 50 million of them. Let's see, Java 11. Let's see if the fork join pool has a statistic for how many actual tasks were sent to it. It probably does.
Q submission count.
No, they have not yet begun. I want to know the total. What I really want is a total number. Like, what were the total number of submissions? Maybe it doesn't give that a summary statistic like that. Doesn't look like it has a statistic for the total. Oh, wait, but well, maybe it has it as a sub. Maybe it inherited from the.
ToString has a task count. I don't know if that's exactly.
Oh, maybe. See, I did, but I thought I used ToString. What? Let's see.
What did you use? You used ToString.
Use ToString.
I did use ToString, but I didn't get it. Yeah, I used ToString.
Strange.
Worker and task. But what did we get out for task count?
Tasks, 0.
0. So how many are left?
Oh.
So it gives you the number that are left, not how many were submitted. We want the number that, because that's more useful to a program that's running. A program that's running, that's what I could probably also do. I could just poll, actually, even if I go back, that's something I could do in this other one. Like in this one, the one that I don't know how to shut it down, I could probably write a little loop. This would be the easiest thing to do. Write a little loop that just queries the pool to ask how many tasks are left in it. And when it goes to 0, I can assume that the pool is done. Okay, so
that's a safe assumption.
Yeah, that's because we know that we're not submitting anything to it afterward. So probably I could, instead of doing a shutdown this way, I could just write a loop to just query the pool. Just query the pool and say how many.
Have it on like a 1 millisecond resolution, which is
even a couple milliseconds. So the pool is okay. Executor service is the type of pool it is.
Oh no.
But this one doesn't have statistics.
Oh, wait.
Unless
it has to though, because how does
the ToString method
keep track of what's running?
Well, it may not make them available to you.
Be weird. And it doesn't have a custom ToString.
No. Well, the fork join pool came much later than these, and they learned. They probably kind of realized that they were missing something here, unless it's okay.
Executor is the interface.
See, executor only has the execute, so it's not going to be in it. That's a real. See, fork join pool is a subclass of this guy. Okay, maybe this thread, I don't know, maybe we're actually a thread pool executor. It could be that we actually are a thread pool executor. Get active count. Yeah, so probably we're probably actually running this kind of thread pool. And I could probably use any one of these. Probably the get active count would be a good one. Wait till the get active count goes to 0. Let's see, what else is there?
It's got the
Get task count.
Yep.
Yeah, I could do get task count. Okay. Okay, like this is the total number of tasks that have been scheduled for execution. That's what we want from the thread pool, the total number of tasks. But this function seems to be in this thread pool, but it didn't seem to be in the fork join thread pool. It's funny how they if you go to the if you go here to the tree, you can see what's a subclass of what. There's the thread pool executor. See, neither one, they're not quite related to each other. A fork join pool is an abstract executor service, and a thread pool executor is an abstract. But so they're not quite compatible with each other. There's things in the fork join pool that aren't in the thread pool executor. So for example, the thread pool executor lets you call get task count, but the thread pool, the fork join pool doesn't have a get task count. Okay, so somehow the designers of these things thought different. They just thought differently about these two different thread pools, and they give you different ways of asking questions about them. Okay, but for this one, I could use get task. Well, I could use get. Where was it? Get active count. Once the active count goes to 0, there would be no active threads in the pool. I could shut the pool down. Okay, so then I could get this one. I could make this one work better. I could make this one have a good way to shut down by polling I could poll the thread pool until it doesn't have any more active threads and then shut it down. Okay, right. And it'll probably end up being, I don't know if it'll end up being as fast as the fork join, probably not. It probably won't end up being as fast as fork join, but then I'll be able to compare that, because right now I don't even get a final runtime because the thread pool never shuts down. Okay, all right, so it's interesting to see the difference in these thread pools, and this piece of code is pretty sophisticated in the sense that there's 2 levels of tasks being put into a fork join pool. One level of task is one that's forking off the sub-levels of task. Notice it's not, what I liked about this is, if you read about fork join pools, almost everybody talks about them in terms of their use with recursive functions, as if fork join pools came from recursion. And almost everybody, and I was actually fooled by this until I wrote this, thinking that fork join is tied to recursion, because that's the way everybody kind of, and even here it says that recursive action is part of the fork join interface. A fork join pool works with recursive actions, but there's nothing recursive in this example. It's actually an IO example. And there's nothing recursive. Once I open a file, this task opens a file, and then it just iterates through the file, forking off new tasks that aren't recursive tasks. They're just little subtasks. Each new forked off task is just reading one buffer. So there's nothing recursive about this. I'm iterating through this file, forking off a task for each buffer. And then each buffer will fork off a task for, this guy forks off a task for each file, then a file forks off a task for each buffer. Not very recursive at all, okay? But the fork join pool works real nice. And we saw that it does work. One of the reasons why I think it's gonna be faster than the other one is because the work stealing, we see that it actually did a fair number of work stealing the work stealing is a good way of load balancing. So the fork join pool is probably doing very good sense of load balancing among all the cores, whereas there is no load balancing in the other pool. When you use a regular pool, there is no, pardon me?
Oh, sorry, I'm just clearing my throat.
There is no load balancing between the cores in the other kind of thread pool. So the fork join pool's got two advantages. It lets you submit, once a task is in the pool, it can continue to submit tasks to the pool even when the pool is shut down, and allows the work stealing to do load balancing. So my guess is this one probably won't be quite as fast as this one when I fix it so that it can be shut down properly. Okay. Now, let me show you how I think there might be one last way to speed up this fork join pool, this last one. Okay. There's another standard trick up programmer's sleeves for speeding up things. Okay. Whenever you're doing file I/O, there's a standard technique called memory mapped files. Okay. So I actually wrote the code. I don't know if you guys have seen this before, but I wrote the code for memory mapped I/O. Memory mapped I/O is something that actually comes out of the operating systems course. It's when you use the virtual memory system's paging system to do your I/O. Okay, now let me show you a baby example of this. Okay, I'm going to go way back to the beginning when we were just counting bytes in a file. Okay, like, we have, here's two programs that counted bytes in a file. Okay, we open the file and we just iterate through the file. This one iterated through the file buffer by buffer. Okay, and this one iterated through the file. Let's see, try to remember. Oh, this one iterated through the file byte by byte, so it's much slower. Okay, this one iterated through the file byte by byte. This one iterates through the file buffer by buffer. Okay, so let me run this. This is on the 2 GB file, not the directory of files. Okay, so it takes 700 milliseconds. It takes a little less than a second to read that 2.3 gigabytes worth of data. Okay. Right. Now remember, what that's doing is it opens the file, then reads one buffer at a time and just counts how big the buffer is. But the whole file is being read into memory. The file is being read into memory one buffer at a time. Okay. Now let me speed that up by doing a memory mapped version of this. Okay. Okay. When you memory map a file, essentially what you tell the operating system to do is to put the file in your virtual memory space. Like, let me draw you a picture. Okay. Been doing this in the operating system class. In the undergraduate operating system class, I'm teaching page file systems. And what we're really talking about here is a page, is something called, it's got to do with the paging virtual memory system. Okay, so think of it this way. Here's a virtual memory space. And a virtual memory space is chopped up into pages. So here are the pages of virtual memory. So I'm just going to imagine I have a small number of pages of virtual memory. So here's a small number of pages of virtual memory. Okay. And this is my virtual memory space. Okay. Now, suppose one of these pages is my code page. So imagine that all the code is in this page here. So this is code. Okay. Suppose I want to open a file. What a modern operating system like Windows lets you do is, instead of opening the file for I/O, you can just say to the operating system, map the file to this region of virtual memory. So I'm going to do it like this. I'm going to suppose that the file is mapped to here. So it's a big file, so it'll be mapped to a bunch of contiguous virtual memory pages. So here's my file. My file now appears as an array in memory. I tell the operating system, allocate virtual memory pages to me from here to here and use this file as the data in those pages. The file now doesn't look like a file to my program. It looks like a big array in memory. Now, what the operating system does, you have a page table and you have physical memory over here. Okay. Now, physical memory is a bunch of pages, just like virtual memory is. Physical memory is a bunch of pages. Let me try to draw them real quick. How many of you have ever seen a description of memory map files?
I have.
Did you guys talk about these in the operating systems class?
Yeah,
Yes.
that's what our project is for coding.
To do memory map file, to work with a memory map file?
Yeah, well, we're supposed to take the virtual page and turn it, use the the TLB and then LRU and
We're not quite doing that in our operating systems.
No, because you
class.
can't do anything with the TLB. That's owned by the operating system. Microsoft's not going to let you even touch the TLB.
yeah, we're not using theirs. We're making our own in the program, and then
You're writing a
Address
simulator.
translation
yeah, we're
from-
simulating. We're simulating it.
No, I'm talking about real. I'm talking about
Oh.
really using
Oh, no.
memory map file. Okay, so here's how it would look. Okay, so this is physical memory over here, and this is virtual memory over here, and this is the page table over here. Oops. And over here is the processes page table. So here's the page table. Okay. Now, the file is 1, 2, 3, 4 pages in size. Okay. So here's the page table entries. Here's a bunch of page table entries. And then one last part of this picture would be the hard drive. The file itself is over on the hard drive somewhere. So here's the hard drive. So this is the disk drive. The disk drive is chopped up into sectors. Now remember, one of the most important ideas in computers is that a sector on the hard drive is the same size as a page of virtual memory. That's so there can be a one-to-one mapping between pages of virtual memory and sectors on the hard drive. Okay, so here's the 4 sectors on the hard drive of my file. So here's my file. This is my file on the drive, and it's 4 sectors. Okay. Okay. Imagine, so these 4. Now, what's going to happen is that I'm going to tell the operating system that these files here should appear as virtual page frames over here to back up this stuff over here. So make one more row in my page table. Okay, so my page, I have 1, 2, 3, 4, 5, 6, 7 pages. I have 1, 2, 3, 4, 5, 6, 7 rows in the page table. The last 4 rows are supposed to be the hard drive, are going to be this file. Okay, so what I'm going to do is file 1, file 2, file 3, file 4. Those are the 4 blocks of the file. So there's file 1, file 2, file 3, and file 4. Suppose the operating system puts file 1 here. Suppose it puts file block 2 here. puts file block 3 here, and puts file block 4 here, okay? And then the page table entries will be, see, file block 4. File block 4 is going to be in, see, this is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So page table entry here is 9. Is that readable? No. 9, okay. File block 3, the third file block is in entry 2. File block 2 is in entry 0, 1, 2, no, that's entry 1. So I started counting as 0, 1, 2, 3, 4, 5, 6. This is 6. And then this would be 0, 1, 2, 3. Okay, so if you do this, Windows lets you do this. Windows lets you tell the operating system, make this file in the hard drive, make it copied into memory as page frames in memory. So this sector of the hard drive is loaded into that page frame in physical memory. That sector of the hard drive is loaded over here. This sector is loaded over here. This sector is loaded over here. But they look like a contiguous array to my program. My program now looks like it can read this file by just stepping through this array. Okay, this
and
is
hopefully,
pardon me?
And hopefully the transfers from the drive to the memory are more efficient than whatever we are getting out of stuff like buffered input stream.
Yes, exactly. The virtual memory system is one of the most tuned pieces of the whole operating system. So when you map this file into the virtual memory system, the file I/O is optimized incredibly fast. It's way faster than opening the file using the file system. The operating system does this blazingly fast, okay? It does memory mapped file I/O blazingly fast, okay? So, so this is what a memory mapped file looks like. This is the idea of a memory mapped file. Now, how does it end up actually working for us, okay? If we go over here, this was a fairly fast run through of the file. You know, it took 700 milliseconds to read 2 gigabytes of file. Now memory map it. Three times faster.
Oh.
See, 3 times faster. It ran in under 300 milliseconds. Okay, so actually about twice as fast. About twice as fast. A little bit better than twice as fast. Pretty impressive. Okay. Then I printed out some other stuff here. And also, I'm doing this inside Java. I think it would be even faster if I was doing this in C. Java lets you memory map files through their own interface. Java has an interface for memory mapping files. There's something called mapped byte buffers. They call them mapped byte buffers. Okay?
I always kind of figured that stuff like scanner and buffered IO stream were just doing this already in the
No.
background.
Oh, if you're interested, scanner is the slowest, stupid piece of junk you can imagine. I spent the whole weekend testing these things. I wrote a whole bunch of, because I sit there wondering like what is the fastest way to get IO in Java? And what surprised me is that scanner is a piece of, well, it's not a piece of junk. It does what it's supposed to do. Scanner is supposed to have been, you know what, scanner was actually designed for CS1 classes to make it easy to do IO in a freshman class. Turns out to be absurdly slow, okay? So memory map files about 1,000 times faster than scanner. And scanner is about 100 times slower than the better ways to do IO. Okay, so let's see. Let me see if this is the one. Yeah, here's one. Here's counting lines using a scanner. Here's counting lines using a scanner. I'll let that run for a while.
Oh.
Well, I can't run, yeah. It's gonna take about think it's 3 or 4 minutes to read this 2 GB file. On the other hand, if I count lines with a memory mapped file, well, I can't run 2 at the same time because the file system, yeah. I'm going to kill this. This is going to take several minutes. If I use a memory mapped file, two and a half seconds. Scanner is going to take about 3 minutes, and a memory mapped file takes 2.5 seconds. Okay. And then if I'll put these up on the website, then I went through, this one uses scanner, then this one uses something else, and this one uses something else, and this one uses something else. They keep getting faster until you get to the memory map file, which is the fastest. Yeah, there's a progression of better ways to do I/O in Java. And if you can do it in a memory mapped way, that's usually a good way to do it. Okay? Okay. But let me show you. It's not as simple as I'm making out to be right now. Okay. Okay. Scanner is ridiculous. Scanner doesn't work at all. Okay. But let's look at some of these other count line programs. Okay, here's the one that counts lines using a memory map file. Here was the second fastest one that counts lines using a buffer. I do my own buffering on an input stream. It's the same speed as the memory map file. The memory map file did not speed this thing up. Well, no, I'm sorry. No, it didn't.
No, it's about twice as fast.
Wait a minute. It was still twice. No, oh no, it was the search algorithm. I'm sorry. Yes, counting lines and counting bytes worked real well with the memory map file. Okay, the memory map file worked really, really well. But then when I went to the search algorithm and I memory mapped the search algorithm, the memory map file didn't speed me up at all. Okay, so here is a fast search using buffered I/O. Here's a fast search using buffered I/O. Oh, I'm sorry. I have to give it the stat. I have to tell it where the file is.
Oh.
Okay, there's a fast search using buffered I/O. It took 5 seconds to search the 2 GB file for all the aardvarks. Okay, now here's the memory mapped, non-parallel, sequential. Lost where I am. Search sequential using a memory map file. This was searching sequential. No, did I open the wrong thing? Oh, I didn't want to open them. I'm sorry. I was supposed to use, I want the sequential memory mapped search. Here's the fastest sequential memory map search, version 4. Okay. Okay, takes 6 milliseconds, almost 7 seconds. That's the fastest sequential buffered I/O version. That's using buffered I/O. Then here's the memory map version. There's no real speed up. Somehow I lost the speed up. When I switched from counting lines to actually doing a little bit of searching, I lost the speed up. And I think I know what I did wrong. Well, I think I know where the loss is. Remember when we look at this picture, our file looks like it's just a big array in memory. The whole point of memory mapping a file is that you don't use I/O operations. The file is just a big array in memory, okay? Java does not make it look like a big array in memory. Java makes it look like an object in memory. So this is the memory mapped byte buffer. You have to call this get method on it. And I think I'm not using the get method right. I think it's these get methods that are slowing me down. Okay, see, in the sequential version, I'm using a real array. So that's a real array access. This is not quite, I really don't know why Java doesn't just give me an array. You know, it's in C, if we were doing this in C++, after we memory map the file, it's an array. You just use array access from then on, which is super, super fast. But in Java, for some reason, after they memory map the file, they don't give you an array. They give you this thing called a memory map. They give you a thing called a mapped byte buffer object.
You can just ask it to give you the array.
I can't find it in the API.
It's called array.
No, but that's going to copy the array for you into memory. That's
oh,
not
it does a copy?
Yeah, yeah. At least as far as I can tell, it's a copy. You know, it's not the underlying.
Modifications to this buffer's content will cause the returned array's content to be modified and vice versa. No, it's the same thing. It's not a copy.
I don't think so.
That's what the documentation says.
Let's see what I want to look up.
Byte buffer.
No, well, you're looking at byte buffer, the byte buffer interface. See, that's the key word. These are not backed arrays. These are not backed buffers. Here, let me go back and run the very first memory map program, the one that just counts bytes. Has array, false. Okay. A memory map file is not backed by an array. You'd think it would be, but it's not. See, right there, it tells me has array, false. So you have to read the documentation real carefully. You can't read the documentation superficially. You got to read it real carefully. Java has a very specific meaning of what it means for a byte array to be backed by an array. And memory map files are not backed by arrays. Even though it's this picture, it's not backed by an array. Okay, and it's telling, see, it says that. It's what's called a direct file. Now, the direct file is important. It's a direct thing, which is true, which means that, forget what, that's the thing that means it's fast. It's direct, but it's not backed by an array. Okay, so as near as I can tell, the only way to get at the data in the mapped byte buffer is to call the get method. But I have a feeling I'm using get method with an index. I think the fast way is to use get method without an index.
There is supposedly a bulk get method.
That does copying. But see, I don't want to do a bulk. I want to see, you know, I want to compare to all, I want to step through the array and see if I have aardvark. Now, it might be possible for me to do a small bulk grab of memory and then step through it like this. I'm going to try to do different things, but somehow the memory map version is not faster than the non-memory map version. And it should be a little bit faster. It should be a little bit faster. Now, that's one thing to do. Then now go back to this. Earlier we were talking about the searching for files here, okay, with the thread pool, with the fork join pool. Okay, I think it might be possible to speed up. This task here might be made faster if it could be memory mapped. So I'm wondering if I could memory map the file first, then chop it up into pieces and submit them to the fork join pool. But that won't help if I can't solve the problem of why the memory map file doesn't seem to be as fast as an array. So I'm going to see if I can figure out why the memory map file isn't acting as fast as an array. But if I can get the memory map file to act as fast as an array like it would in C++, then I should be able to speed up this by memory mapping the file rather than using I/O. Instead of opening the file and reading it, I can open the file and I can memory map the file. Instead of opening the file using the I/O system, I should be able to memory map the file and then step through the file as a memory mapped array. So that might speed this up even a little bit more. Because the ultimate speed in almost all programming environments, the fastest I/O is almost always going to be memory mapped. You know, whenever you read performance literature and people talk about what's the fastest way to do anything, it's going to almost always be memory map the file, then access the array, underlying array. And in C++, I've written it in C++, it works. This is the first time I've ever done memory mapping in Java, and I'm a little bit stumped by why Java is not giving me, why it's making me do function calls. Notice that these are, one problem is these are function calls, unless the compiler's really super clever, function calls are not as fast as array access. So right off the bat, there's something suspicious there. Array accesses are fast, function calls are not quite that fast. So maybe this function gets inlined. Maybe the compiler knows enough to inline this function, but then there's this index here. I'm thinking the indexes might be causing problems. Using the index might be causing something. Yeah. So I have to, if this was C++, this piece of code here would look exactly like that. It would just be an array access, and it would be blazingly fast. I'm not sure what's going on with it's faster. Well, it's not slowing us down, but it's not speeding us up either. Okay. All right. So what's interesting is just how when you get to where you want to do something as really fast as possible, there are a lot of tricks you can use. Memory mapping files, fork join pools.
On the processor end, once we actually get proper memory mapping to an array, could we use a single instruction, multiple data instructions try to grab more data and compare it?
Yeah, if Java will let you. I don't know if Java does SIMD instruction.
You might just be able to map, say, buffers of characters.
Yeah, you might be. But
large words.
But it only works if you can actually execute the SIMD instruction in the CPU. If the Java virtual machine won't give you access to the SIMD instructions, my memory is that that's an ongoing project in Java.
I don't know. Whenever I look up stuff like that, I just hit brick walls of nothing.
Well, that stuff's hard. See, SIMD optimizers for the Java virtual machine. Okay. I don't know if they work yet.
Like most of the time, the answers that I get is that if it's available, your compiler is doing it for you.
Yeah, usually if it's available, the compiler's doing it already. But I don't know if Java compiler does it yet. Yeah, I don't know if the Java does if Java does auto parallelization of SIMD instructions.
InfoWorld, Oracle and Java seek to build a Java API for SIMD and support. Second link. The second link on that page.
Yeah, but I don't know if it's there yet. See, this was I know that I know it's been talked about. I don't know if it's actually, I don't know, see. Project Panama. I think that's still an ongoing, and that's that's a different compiler. That's the Graal compiler, which is not the default compiler for Java. So this may all be this may all still be one big, ongoing project. The Graal compiler is a new compiler that's being written. That's not, it's ready, but it's not the default compiler that comes with the JDK. And so I don't think this is part of the JDK that we're using. I don't think it is yet. Okay. Yeah, it's a big mess. Yeah, it's interesting. Yeah, it's on the bleeding edge of what languages like Java can do. If you're willing to use C++, which a lot of people are, this stuff's pretty straightforward. You know, SIMD instructions in C++ are a lot more straightforward. Just like memory mapping of files a lot more straightforward in C++. But Java being a virtual machine with a just-in-time compiler adds a layer of complexity that's kind of tricky. So, you know, the memory mapping, I got a good performance boost on the counting lines, but I lost the performance boost when I actually did a search through the file, and I'm not sure why. And you're right that if I can actually get this to be, you know, I might be able to get this to be SIMD. You know, maybe.
One way to get around just not using SIMD at all might just be to do bit masking.
Probably not. I mean, SIMD is built into the CPU, so you're getting the speed improvements of the CPU itself. If you're going to do bit masking, you're not going to get any. The CPU is not helping you.
Like you bit mask on as large of a word as you can possibly,
which is 64
get.
bits. But the SIMD instructions are 1,000 bits per word. You have to remember the SIMD instructions are 1,000 bits. So yeah, you're just not going to get the performance of the SIMD instructions if you try to muck things up. You know, the SIMD instructions have 1,000-bit words. I think what they call, I forget what Intel calls them now.
I was gonna say you'd get like maybe like an 8 times increase because you'd be doing 8 characters at once.
Or even more than that. I forget what the largest word. I forget what the largest word they have is. See, there were 1,000 bits.
AVX is designed to support 512 or 1,024 bits in the future. Right now, they look like
this was in 2011. Okay, I think they've now gotten to 1,000-bit vectors. So that means that the CPU operates on 1,000 bits at a time. Yeah, that's really fast. Okay, that's what you'd like to get at. Yeah, but I don't know if the Java virtual machine is going to get at that. Yeah, it might even only do the 128-bit instructions or the 256-bit instructions. Then eventually,
so in best case scenario, what we've been doing in like just assigning to a whole thread object to do in like a few thousand instructions, this would be able to do it in like 4.
Well, we're using bigger buffers. We're using maybe a few hundred instructions because my buffers are like 1 megabyte buffers, but still you could do comparisons on massive amounts of bits at once. You know, the CPU can compare 1,000 bits at a time. For example, the word aardvark could fit in 1 word. See, so this whole aardvark comparison can be done in 1 CPU instruction. With a SIMD instruction, I would be able to check the word aardvark in 1 CPU cycle. Yeah, because that's not even 512 bits. So that's not even. But then I need access to the SIMD instructions. But you could pack the whole aardvark word into 1 big vector and have the CPU compare that vector in 1 CPU instruction, in 1 cycle. Okay, that's the single instruction, multiple data kind of stuff. So, when you talk about parallelizing, there's so many levels of parallelizing going on, and this is what's called instruction level parallel. So then you're at the low end of instruction level parallelism. Right now we're up here at the high end of the fork join pool, which is task parallelism. And what you really want to do is eventually write code that uses all levels of parallelism at once. If you really write really good code, you can be using every level of parallelism at one time, from memory map files to instruction level parallelism to fork join parallelism.
Now, doesn't that, like on modern machines, come with a risk of just cooking your CPU?
No, of course not.
Like, because I've heard that like AVX instructions can just by themselves cause modern CPUs to thermal throttle.
Well, that's why companies like Intel pay a lot of money for cooling. You cool the system.
Mm-hmm.
Yeah, so if you don't cool it, yeah, you'll probably have trouble. But if you cool it, you're not going to have trouble. So it depends on, like a desk, like this laptop may not survive. You know, maybe this laptop doesn't have the cooling it needs to do that. So if I ran really highly parallelized code on this laptop for a long time, maybe, I kind of doubt it, but maybe it would overheat. But if you're running on a server, the whole point is you should have proper cooling on your server. So if you have proper cooling on the server, you're not going to overheat the cores. You know, but you should provide the core with the proper amount of cooling because it will be doing a lot of work when it does that kind of stuff. But no, Intel's not going to design a CPU that can't do what they sell it to do. So if they're selling it to Purdue University to put it in one of their supercomputers to run molecular dynamics simulations on it, it better well do SIMD instructions all day and all night without melting. But Purdue has to provide the cooling. You know, they have to put it in a CPU case with the right amount of cooling, and then it'll work. It will work, but you do have to make sure you appropriately cool the CPU. Okay, we went over. Let's just stop now. I'm going to put a lot of this code up on the website. I've got a whole bunch of these versions. Like, there's more than there were up there a few days ago, and they do go through different levels from really bad I/O to from really bad I/O to really fast I/O. And it's kind of interesting to see which versions of Java I/O are good and which versions of Java I/O are fast, because it isn't what you'd think from reading textbooks all the time. Scanner turns out to be the worst thing in the world you can use for I/O if you care about speed. Unless somebody knows a better way to use it than the way I've been using it. I'm using it the way most books show it. But if you just use a scanner wrapped around system.in, it's ridiculously slow. And even when I tried to buffer it, it was still slow. Okay, so I'll put this code up there, and you can play around with it. And then we'll on Wednesday we'll see. I'll see if I can solve some of these last problems of like why the memory map file isn't working quite as good as it should. Okay. So, if you have questions about if you have questions about this homework assignment, please send me. If you have questions about the homework assignment, please feel free to ask. Okay, so I'm gonna go ahead and end the meeting now. Good night. Bye.
Good night.